Moving to the next problem, problem 7.51. A car engine burn 5 kg of fuel, which is equivalent to the heat addition, and that is actually QH, at 1500 Kelvin, and reject energy to the radiator and the exhaust at the temperature which is equal to 750 Kelvin. If the fuel provide 400 kilojoule per kg, what would be the maximum amount of work done that the engine can provide? So over here, the heat addition, which is QH, it is definitely not in a direct sense, or it is not written in direct sense, but we have been given the calorific value of the fuel and the amount of fuel. So the calorific value and the amount of fuel. So we have to multiply the, in order to get the total heat, we have to multiply the calorific value of the fuel into the mass of the fuel, and we will be getting the energy which would be supplied by the fuel itself. So we have got the 200,000 kilojoule of heat which is added in the engine. Now, assuming the correct efficiency, the maximum theoretical work done, so efficiency would be equal to 1 minus TL by TH. If you can check, like we do have like TH over here, we do have got TL over here, just putting the value, we will be having the efficiency of the Carnot cycle. Now the amount of work done, which with the maximum amount of work done by the engine, so the maximum amount of work done would be the efficiency multiplied by the heat supplied. So the efficiency is 0.5 multiplied by the heat supply, which is equal to 200 kilojoule, 200,000 kilojoule, and we will be having work done which would be equal to 100,000 kilojoule. Moving to the next problem, problem number 7.94. An ideal Carnot cycle with an air in a piston cylinder has a high temperature at 1200 Kelvin and a heat rejection is at 400 degrees centigrade. During the heat addition, the volume triple. Find the two specific heat transfer, which is QH and QL, and the cycle overall, or the overall efficiency of the cycle. So let's say like we assume like we have got the Carnot cycle, assuming like we have got the Carnot cycle. We have not done the PV diagram of Carnot cycle. We will be doing in the next lecture. But let's say we have got a PV diagram, and in a PV diagram we do have like two temperature reservoir, which is one of the reservoirs is temperature TH and the other reservoir is at temperature TL. So it's a like the high temperature reservoir is at 1200 Kelvin and the low temperature reservoir is at 400 Kelvin. So for a high temperature, it's a like the when we are adding the heat into the system, which means like we are adding heat from the high temperature reservoir QH. So the volume of the system or the volume is double. So that means the volume is triple. Sorry. So if we have got V1 over here, so we will be having a volume at state 2, which will be equal to 3V2, 3V1. So that means like the volume is triple now. So let's say finally, let's say move towards the solving the problem now. So the efficiency of the Carnot cycle is easy to find. So efficiency is equal to 1 minus TL by TH. So we do have got the TL over here and we do have got the TH over here. So putting the value and we will be having the efficiency which is equal to 0.667. But to find the specific heat transfer, let's check like what kind of different formula we can have. So the work done is, or if I say like the efficiency is equal to 1 minus TL by TH. So we cannot find any like the specific heat from this formula. The other, if I say like other efficiency was work done by heat transfer. So that means like that would be something like this. We do not have got the work done as well. We do not have got the QH as well. We do have got another formula which is work done is equal to QH minus QL. So we do not have got the QH over here We do not have got the QL over here, not the work done. So obviously this formula is also not valid. So that means like we are definitely looking for a formula which would solve our problem somewhere here. Let me rub it down. So in a statement, it's a like the during the heat addition, the volume triple. So when we are supplying heat to the system, it's a like the volume is going to increase by threefold. So we must have got an equation which relate the heat transfer and the volume change. Now that would be a little bit tricky over here. So if you can check like in a Carnot cycle, when we were supplying heat to the system, that heat was transferred in an isothermal process. So that means like in a supplying heat, the process was isothermal, and we do have the work done in an isothermal process. So work done in isothermal process is log like PV log of V2 by V1. If you remember that one from the previous classes, PV is equal to RT. You can also say like W is equal to RT log of V2 by V1. So that means like the heat transfer is the heat transfer QH would be equal to W in an isothermal process. And if I can say like if you remember from the first law of thermodynamics, change in internal energy is equal to Q minus W. And if you remember, like internal energy is a function of temperature. So if the process is isothermal process, so there is no change in temperature, so the internal energy would be equal to 0 and Q would be equal to W. That means like the in an isothermal process, the heat transfer is equal to the work done. So that means like in our equation, which was the work done equation, is now actually equal to the heat transfer equation. So QH would be equal to RT log of V2 by V1. We do have got the R for the air, which is actually somewhere given over here. Temperature TH of the high temperature reservoir, which is 1200 Kelvin. The volume V2, which is equal to 3V1, and volume V1, putting the value, and we would be having the heat, which is actually at QH. Now finding the QL would be definitely easy. If you remember from the previous lecture as well, TL by TH would be equal to QL by QH, somewhere like this. So just putting the value and you will be getting the answer, which will be something like this. Moving forward to problem number 8.28. Find the entropy for the following water state and indicate each of the state on a TS diagram relative to two-phased region. We have got part A, which is at 20 degrees centigrade and 10 kilopascal, and we have got part B, which is at 20 degrees centigrade and 10,000 kilopascal. So 0.1 megapascal and 10 megapascal, if to be very precisely. So first thing first, in to finding the where the phase is lying, we have to go to the steam table. So looking at the steam table at 20 degrees centigrade and 10 kilopascal. So 20 degrees centigrade and 10 100 kilopascal. So at 20 degrees centigrade, we have got a pressure which is equal to 0.002339 megapascal, which means like we are having a pressure equal to 2.339 kilopascal. Looking at our condition, so our both condition, our pressure is greater than 2.33 some obviously. So that means like both of our region are in a compressed liquid state. So as the pressure is increased, we will be moving in a compressed state. So both of the region are in a compressed state. So we have to move to the compressed region and make sure like you like in this steam table, a semi compact region, we do not have got the compressed table, but if you look at your own book, you will find the compressed region. So just moving to the compressed region, you will find the value of both the um, entropy entropy at 20 degrees centigrade 100 kilopascal, and entropy at 20 degrees centigrade and 1000 kilopascal. Let's check like 20 degrees centigrade and 100 kilopascal. So that would be not in this table as well, and 20 degrees centigrade and 10,000 kilopascal. So 20 degrees centigrade and 10,000 kilopascal is already here. We have got a 20 degrees centigrade. So entropy at 20 degrees centigrade and 10,000 kilopascal would be equal to 0.2946. So checking 0.2946. Not sure like how do we okay, so that mean like that was not in a steam table. So they have taken the entropy of the saturated liquid at the 20 degrees centigrade. That means like if you're looking at the steam table at 20 degrees centigrade and looking at the entropy at 20 degrees centigrade of the liquid, so that is 0.2965, and that would be equal to 0.269 would be equal to entropy at 20 degrees centigrade. Although it's definitely not a correct method, but more or less it would be equal to the little bit equal to the that value. Moving to the next problem, problem number 8.30. 2 kg of water at 120 degrees centigrade with a quality X equal to 25% has its temperature raised 20 degrees centigrade in a constant volume process. What is the new quality and the specific entropy? So we have got a condition in which we have got a liquid which is at 220 liquid water which is actually at 120 degrees centigrade. Now at 120 degrees centigrade, the quality of the water is 25%. It's like we are increasing the temperature, raising the temperature to 20 degrees centigrade more now, but the process is constant volume process. So obviously if you're looking at if you are increasing the temperature, so it will be actually increasing the pressure inside the vapor dome. So that means like at 120 degrees centigrade we are having a liquid which is at 25% quality. We have increased the temperature at 20, we are raised the temperature 20 degrees centigrade, and now we have got a temperature which is equal to 140 degrees centigrade. So it's like what is the new quality at 140 degrees centigrade, and what would be the specific entropy at 140 degrees centigrade. So first thing first, we have to find the volume at 120 degrees centigrade, because as I say like the volume would remain constant. So if we are moving to the next state, so we must have got the condition which would be known in the state 2. So finding the volume, and if we have got the inside the vapor dome, volume would be equal to V is equal to Vf plus X Vfg, and that would be at 120 degrees centigrade. Finding the volume Vf and Vfg, looking at the steam table at 120 degrees centigrade. So at 120 degrees centigrade, if I'm looking at this one, so we have got the volume table which is actually at second. So we have got the volume Vf at 0.0010603 and Vg at this one. Putting them in here, and we would be finding the volume which would be at volume at 25% quality. Now this volume would remain constant. So when this volume remain constant, by increasing the pressure, pressure obviously, but by increasing the temperature at 140 degrees centigrade, now we would be having two different volume value, and that would be volume Vf at 140 degrees centigrade. We would be having a volume Vf, and we would be having a volume Vg. Now putting that Vf Vg again in the equation somewhere on this equation, but for the 140 degrees centigrade, and this volume, which is constant, from 120 to 140, you can find the value of x, which would be equal to 0.4385. Now for the entropy, entropy would be equal to S is equal to SF plus X SFG. So we have already found X over here. So looking at the steam table for the entropy, that means like for the 140 degrees centigrade, entropy at liquid would be equal to 1.7393, and at entropy of the vapor would be equal to 6.9293. Putting them value in here, you can find the entropy at 140 degrees centigrade. Let me confirm it again. So we have got the entropy of a liquid, which is 1.739. Entropy of the liquid, it is 1.7739 over here, and entropy of the gas or the vapor over here, it's written 5.1908, while it seemed to be some problem over here. Oh, sorry for that. It is not SF, it is SG, it is SFG. So obviously you are subtracting the SF from that one, so obviously it will be 5.1908. So yes, it's correct. So just putting them, and you will find the entropy at 140 degrees centigrade. Now moving forward to another problem number 8.65. A piston cylinder contains 2 kg of water at 200 degrees centigrade and 10 megapascal. A piston is slowly moved to expand water in an isothermal process to a pressure which is equal to 200 kilopascal. Any heat transfer takes place with the ambient at 200 degrees centigrade. So if there is heat transfer, it is at 200 degrees centigrade. And the whole process may be assumed reversible. Sketch the process on a PV diagram and calculate both the heat transfer and the total work done. A little bit tricky question anyway, but let's find the different, or well, let's find the different condition which is given, or different state which is given. State number 1, which is at 200 degrees centigrade and 10 megapascal. At state 1, the water is expanded, and that is expanded to 200 kilopascal. That expansion means like the volume would be increasing while the pressure would be dropping. So it is expanded to 200 kilopascal while the temperature remain constant, that is equal to 200 degrees centigrade. The process is reversible. That means like if you are looking up for the equation of the any equation of the heat transfer or something, we would be looking at the reversible equation. Now finding the heat transfer and work done. Before we go to the to find the heat transfer and work done, let's check like what kind of a different formula we would be having. We do have like energy from the energy equation from the first law of thermodynamics. We do have got the energy equation, which is equal to change in return energy would be equal to heat transfer minus work done. From the second law of thermodynamics, change in entropy was equal to dq by t, sorry, and that means like it was the entropy change, and that was entropy change in a reversible process. So looking at the condition again, let's check the state 1. So we do if I say like we have got 200 degrees centigrade and 10 megapascal, so checking the table at 200 degrees centigrade. So at 200 degrees centigrade, if you look at the pressure, that pressure is equal to 1.5547 megapascal. So that means like our pressure, which is 10 megapascal, 10 megapascal is obviously greater than this pressure, which is equal to 1.5547. So if it means like if the pressure is greater than the given pressure in the pressure saturation pressure, so that means like we are in a compressed region. So state 1 is in compressed region. While looking at the second part, which is, or the second state, the pressure is 200 kilopascal, which is equal to 0.2 megapascal. Checking back, so at 200 centigrade, 200 degrees centigrade, if we have got a pressure at 0.2, so that means like 0.2 is less than our saturation pressure, so we are in a superheated region. So we have got two conditions now. So state 1 is in a compressed region, while state 2 in a superheated region. At state 1, the pressure is greater than the saturation. At state 2, the pressure is less than the saturation. So we are moving from the compressed region towards the superheated region. So now going to the compressed table and going to the superheated table, we can find the volume V1, internal energy U1, and entropy S1. That would be in a compressed region at 200 degrees centigrade and 10 megapascal. Somewhere here, 200 degrees centigrade and 10 megapascal somewhere here. And for the steam table at superheated condition, so obviously we're looking at the superheated condition, we will be having volume, internal energy, volume, entropy, internal energy. If the internal energy is not given in this table, so you can find the internal energy is equal to U is equal to H minus PV. If you remember the formula for the enthalpy was U plus PV. So that means like if you are finding the U, so that would be equal to H minus PV. So in this condition, all the pressure, volume, and enthalpy would be given, and you can find the internal energy. Now putting that internal energy, not for a while now, I think, because if you put it internal energy over here, so you cannot find anything from this equation because we still have got the two unknown in it. So let's take the other equation, which is the equation of the entropy. So in equation of the entropy, if we put the value of the entropy over here, the temperature, which is 200 degrees centigrade, so we can find the heat transfer. So that means like the heat transfer would be equal to T multiplied by the change in temperature and multiplied by M. That means like if you're looking for the total heat transfer, mass is already given. So Q would be equal to this much, and now putting back this Q in the above equation of the first law, W would be equal to Q minus internal energy, and you can find the equation, the work done as well. So heat would be equal to 4910 kilojoule, and work done is 1290.3 kilojoule. Now moving forward to another question, that is question number 8.91. A rigid tank contains 1 kg of methane at 500 degrees centigrade and 1500 kilopascal. It is now cooled down to 300 Kelvin. Find the heat transfer and change in entropy using ideal gas. We can have the same kind of an equation, the equation of the first law and equation of the entropy, and entropy of the, but that means like entropy of the ideal gas. Please refer to the previous classes where we derived the equation of the entropy of the ideal gas. This is the problem of the ideal gas, so we will be not using the steam tables. Also, it's like a rigid tank. That means like there is nothing moving part, so that means like there will be no work done. So the volume is constant, so there will be no work done. So your equation of the first law, which is in change in internal energy Q minus W, which the work done would be equal to 0. Now the only thing would be equal to the change in internal energy would be equal to heat transfer. The change in internal energy for the ideal gas, if you remember, that is equal to CV delta T. So putting that in here, the heat transfer would be equal to CV delta T. CV for methane. Make sure like it is either given or you do have like a property table for the methane over here. So methane is CV for methane is 1.736. T2 is 500 Kelvin minus T1, which is 300 Kelvin. So that would be equal to uh, T1 is equal to 500 Kelvin, while T2 is equal to 300 Kelvin. So that means like 300 would be the temperature at the exit, which is cooling down, and 500 would be temperature initial pressure temperature. So you will be having the heat transfer will be equal to minus 347.2. So that means like the system is cooling. For the change in ideal gas, please refer to the notes, which is the deriving the equation of the entropy of the ideal gas. Putting the value in that one, you will find the the value of the entropy of the ideal gas. I hope you understand this lecture. If you do have some problem, please make sure like you just post in the classroom, and I would be able to answer that question. Have a nice time. Thank you very much.